This is our second lesson for Chapter 2. It's our second look at limits for calculus, the engine, if you wish, that makes the race car of calculus go. And today we're going to look at something called one-sided limits, and then we'll see how they can be used to talk about asymptotes, both horizontal and vertical asymptotes. And just to kind of get into this issue of one-sided limits, I'm going to actually show you a function that happens to have an absolute value kind of embedded in it. So it's a rational expression, but hidden up in that numerator there is this x minus 3 that is inside some absolute value bars. So I wanted to think about what the definition of absolute value of x is. You know, I think we've all seen the graph of absolute value of x, you know, and how it looks like kind of a V shape, you know, if you have x and y. And yeah, sure, when you're graphing it in your transformations unit in Math 12, sure, it looks like that. And we understand that what it's doing is it's measuring the distance from zero. But if you want to try to represent that algebraically, this is one of a couple of common ways of doing that. You could say the absolute value of x is, well, two possibilities here. If you're talking about numbers that are not negative, absolute value of 5, well, then it's just 5. So a lot of the time, absolute value of x is really just the number that's inside the absolute value bars. And that's true as long as you're not playing with a negative number. So you could say, yeah, that's true when the x's inside those bars are greater than, or maybe even equal to 0. That'll just kick a 0 out. But if you're ever playing around with numbers that happen to be negative, we need a new plan. So these numbers will be negative, but we don't want the answer to show up as a negative. So we're going to put a little opposite sign in. And I know when you first look at that, you might say, no. Absolute value shouldn't kick out a negative. Well, it won't. Because if you're on this bottom line of this branch function, then the x's are already negative, like -5 going in here. And this says, oh, well, we'll do the opposite of -5, and that'll actually make it a positive. So algebraically, that's a plan we can use to try to figure out how to deal with absolute values. We're going to take a look at some one-sided limits created by absolute value, and we're going to do it graphically, numerically, and then symbolically on the next page. So I'm going to play with that function, and I'm just going to go ahead and put it into my graphing calculator. Yeah, get that all cleared out. Okay, clear that out too. And this function, it was the absolute value of x minus 3. That's an old TI-83, so it's a little bit awkward here. I can go under the math menu, and if I go over to number, there it is, absolute value, just says ABS. The nicer, newer calculators kind of display absolute value bars. That's great. This one just doesn't do that. So closing the absolute value bar is like closing that bracket. That's done, and then I'm going to divide by x squared minus 2x minus 3. That's the function. And I'm just going to try that zoom 4. And the limit I want to look at is what happens when x gets really close to 3. Right? So let's just kind of zoom in on this here for a second. We're going to be looking right there when x is 3. And if I simply try just tracing my way over to 3, this function, not that it matters for limits, but this function doesn't even exist at 3. It's a big, like, I don't know. We're going to look at what happens just before and just after. And you can see that there's a bit of a little skip there, a little jump as it's discontinuous. And we're going to talk about how you can represent that, how you can write that down mathematically. So let's talk about when you're approaching from this left side, when the numbers for x are a little bit less than 3. And so we're approaching this Wizard of Oz, green curtain like we talked about last day, right? Like, don't look at the man behind the green curtain. Okay, so I'm going to put a little curtain right here. I don't want to look behind there. But I'm going to talk about, well, what happens when I stare at the y value and I start to approach that green curtain from this low side, from the left side. And so here's what we can write. So some people will call this the low limit, right, as we approach from low x's, or we'll call it the left limit as we come in from that side. And we can say, well, it looks like the limit of this function seems to be limiting out to, looking at the numbers, and we'll see on the next page, it's actually -1/4. And I can try just evaluating with my graphing calculator and say, hey, please calculate, a value for me. Right, just going to hit enter there. And I can try putting numbers in that are really, really close to 3, but on the low side. So maybe I'll put in I don't know, let's go 2.99999, like that, right? And it's getting really close to -1/4. Just graphically, it looks like that's where we're going. And last day, we would have just said, oh, well, the x's are approaching 3. Now, that's not quite good enough. Okay, we'll talk about why in a minute. So I'm going to fix that. But let's take a look over on the higher side. What if we were to go and say, hey, let's think about what happens with the y values of the function as you approach this little green curtain here, right, that you're not allowed to look behind. What happens if you approach that green curtain from the high side, right, from the right-hand side? So there's like a higher limit. And by high, I don't mean like y values are high. Well, it turns out they are here. I mean that the x values are high. So we're coming in from the right side of the little green don't look behind curtain. Well, now I'm actually seeing that I don't have the negative in my answer. It's actually 1/4. It's different, right? So I just want to point that out. I'm doing the limit of my function, and I'm noticing that I'm getting this different answer, right? It's just not the same answer. And I was trying to approach 3, but I was approaching 3 from the higher, the right-hand side. So here's how we can actually show that in math. Instead of putting a plus or minus sign in front of the 3, that would say -3. I'm actually going to put a little plus or minus sign after the 3. So here I'm going to go 3 and then put a little minus. And it's just pronounced 3 minus. And this one would be x approaches 3 plus. And what that means is that we're actually going to be on that lower side. Okay, so a little lower than 3. And this means just a little bit higher than 3. A little bit above 3. Now the two answers are not the same. I mean, they both have 1/4 in it. That doesn't really interest me very much. They're just different answers. One's negative, one's positive. And so if somebody asked me, well, hey, what's your answer for what this function is doing as you simply approach 3? I don't have a good answer. I don't have one y value that it's heading towards. The little words up here, as you approach x equals 3 from the left, from the low side, it was approaching one answer. As you approach from the right, it's a different answer. So if they just say, well, what if you approach 3? You have to say, look, there's no good answer. The limit itself doesn't work, but the sided limits do. Okay? And so you've got these one-sided limits that are fine, but not the limit overall. You can use your graphing calculator to create tables of numbers. So here's the exact same function. Right? I could take my calculator and say, hey, let's just do a little table here. So maybe I'll go and set my table up. Say I want to be near 3. You can put whatever you want in for the delta table. Right? That's just how finely the x's move. So maybe I'll go with that and then ask for table. Maybe I'll wiggle the 3 just into the middle here. And what I can see is I've got one answer on this side, this -1/4, and one answer on the other side, a +1/4. It's just not the same value. So in your notes package, I was just trying that with kind of coarser jumps here, right? 0.05 jumps. And then if I want to, I could actually do even finer jumps. Here's 0.01. And you can make the jumps as fine as you want. So here's 0.001, right? Just a little more easy to see that one answer is this number, and the other answer here is different when I get near that don't cross green curtain, don't look behind deal. That's how limits always work. So I could do this whole story numerically, right? If that's all I had was the table, I could look at this table and say, yeah, let me tell you that it looks like the limit of this function. I'm just going to write the same thing that we had before. It seems to be heading towards a y value of -1/4 when x's head towards 3 low. And the answer for this function, when I head towards 3 but from the right-hand side, seems to be a different answer, seems to be 1/4. And if people are like, yeah, but what's the limit? What about just when you approach 3, just in general? What are the y values doing? I'd have to say, look, there's just no agreement on that. There's just no good answer there. So there's a table approach. We've seen the graphical approach at the top of the page. Over on the back side, we can take a look at how you might do this algebraically. I'm not going to lie, it's a bit of a mess. You have to deal with the fact that algebraically, this is maybe your best way in this case here to deal with absolute value of x. This is what absolute value is doing. It's just the number when the thing inside the absolute value bars is not negative. but it's the opposite of the number when it's negative. Okay, so we're going to try out these limits here. On the left-hand side of my page, I'm going to do the left-hand limit. So here we're a little bit low, right? We're less than 3. Just a little less than 3. And on the right-hand side of your page, we'll do the right-hand limit. We'll be a little bit high. We'll be a little bit more than 3. Okay, I'm actually going to do the more than 3 one first. It might be a little bit easier. So the question says, yeah, let's go and do this limit. And when I first stare at it, I'm bothered algebraically by the absolute value bars. They're kind of getting in my way. They're slowing me down here. All right, I've got this absolute value of x minus 3. That's annoying. Down in the bottom there, I've got a trinomial which actually factors pretty nicely. We'll do that in the next line. But I want to come up with a replacement for that red stuff. I don't want to stare at that. But here's the thing. If I'm doing this limit, 3 plus, I'm playing with numbers that are slightly more than 3. On this side of your notebook right now, we'll never have numbers that are less than 3. It's like you have 3.1. And so if you put a 3.1 in right here, then the stuff inside the absolute value bars is positive. We don't need those absolute value bars. They are not working. They're not doing anything on this side of the page. So as long as you know that you're working with numbers that are going to make the thing inside the absolute value bars positive, we can actually remove the bars and say, hey, an x minus 3 looks nicer and it's just as good. The trinomial down there does factor x minus 3 and then x plus 1. And you can imagine where this is going. We are not going to put numbers in that are 3, only close, so we can cancel off the problem. And we're now looking at the limit. I still have to keep writing this. X is approaching 3 plus of 1 on top of x plus 1. That function is perfectly continuous when you're near 3, so go ahead and do direct substitution. You simply insert the 3 in here and say, oh yeah, that answer would be a quarter. Okay, and then down here at the bottom of the page, we can say, all right, here's my answer. Geez, it's the exact same thing we've written twice already. X is going to 3 plus. The limit of the y values is positive 1/4. Great, but now let's try numbers that we might know are going to be a little bit less than 3. Let's go and do the left-hand limit. We'll do that over here. So we've got this story. We're doing a limit. We are assured that the numbers will always be a little under 3. And we are annoyed by this absolute value, kind of wrecking our algebra. And down on the bottom, not bothered by the trinomial. Okay, well, on this side of your notebook, you know we're playing with numbers that are slightly under 3, like 2.9. And if you were to put a 2.9 in here, 2.9 take away 3, that's negative 0.1. The numbers inside this absolute value bar on this part of your notebook, they will be negative in there. So the absolute value bars will be removing that negative by giving you the opposite. So you can say, well, I know I'm playing with that situation. So as long as I'm on this side of my page, why don't I go and say, hey, it'll be like an x minus 3, but it will be the opposite of it. That will make it positive, right? That'll be a positive number now when I put that opposite sign there. Trinomial still factors exactly the same way it did a minute ago. It hasn't changed. And we still have this nice little deal where we can say, well, as long as you promise not to put 3 in and you're only going to be near it, just under 3, then we can throw those factors away. And now when we stare at this question, this fraction of algebra, this rational expression, is just a little bit nicer to work with. It is continuous near x equals 3, so you can go ahead and drop a 3 in there, and we're going to get our negative 1/4. So it's a lot of work to do that algebraically to get to the point where you say, oh, well, let me tell you that the limit of this y value when x is approached 3, but from the underside, the low side of x, is that answer. Now, if people, again, just ask you about the limit, only if the left limit, that left-handed limit, the one we just did, that worked out to be negative 1/4, only if that one equals the right limit, can we say the limit exists. just the limit in general. So in our case, for this question that we're working on, because I use those absolute values, it messed it up. The left-handed limit is not the same as the right-handed limit. So if people ever asked, we would say, oh, well, you know, if you want to know the limit when x just generally approaches 3 and you want to know the limit of the y values, I don't have an answer for you. Right? Just a good old does not exist. All right, well, let's try that out with some pictures here. And I think the pictures will go a lot faster than the algebra that we were just doing there. We'll see if we can get this sided limit deal working. So we've got a graph here. Y's are just going to be the values for that function. And we're going to try playing around, doing a little Wizard of Oz green curtain. You know, don't look at the man behind the green curtain thing. Okay. And so I'm going to start here near -4 and see what we can say about this function. So I've got 4 questions about what's happening near -4. The first one here says, what's the limit of the y values when you approach -4 but from the low side? So that means coming in this way towards that green arrow. Well, it looks like the y value, as I kind of follow the function up, it looks like we're heading towards 2. So I would just say 2. The next question says, well, what's the limit as you approach -4, but can you approach this way this time from the right-hand side? Follow the graph until you get near the green curtain. Hey, that's also 2. And so if somebody said, well, what's the limit just as you approach -4? Well, this is just like last day's lesson. You'd say, well, that's pretty clearly going to be 2. And the next question is kind of like a Math 11 question. It's got nothing to do with limits. It says, well, what if you look behind the green curtain? What do you see? What's the y value? Oh, geez, it's empty. There's a big hole there. So this particular function, this is not a calculus thing. This is a Math 11 deal. No, it doesn't exist. There's no value for the function there. But notice that the top 3 questions are answerable, right? They have answers, 2, 2, and 2. And that's why we like to do this limit thing, because we might be playing with that situation, and we want to talk about where does it look like it's heading to, even though we know it never goes there. Okay, the next column is about what's happening when you're near 1. So let's go and put our little curtain near 1 here and see if we can figure out what's happening. Well, the first question says, please approach 1, but if you could, can you approach from that lower side? Can you come in this way? Okay, sure. As I approach 1 from the low side, it looks like this graph is heading towards 4. The next question says, yeah, let's approach 1. Let's approach the curtain, but can you approach this way? Oh, I guess I'd be following up this curve then. Looks like we're heading towards -2. And if they ask me, well, what do you think about the function for its whole limit? Just like, what's the limit doing in general? I'd say just as a function, the limit doesn't have a good answer. No clear thing there for where it looks like it was heading when it got near the green line. The bottom question says, well, let's actually go look. Like, where is the function? I don't know. Is it even there? Oh, yeah, there it is. It's up there. It can't be in 2 places at once, right, in order to be a function. This time it happened to be up there. In the first one that I did in blue, it just didn't even show up at all. But here it does show up, and it's a 4. Okay, the next one. Let's get near 4, but both from the left and from the right side. We'll try this one out. It's going to go a little faster here now. So for this one, we're approaching 4, and we're going to get there first of all from the low side, coming in this way. Looks like we're heading towards a y value of -2. The next question says, let's go to 4 plus. Okay, heading towards 4 for x, but coming in from the right. Looks like you're heading towards -2. And since they're both aiming towards the same place, right, as I come in both this way and that way, I would say, oh yeah, the limit in general has an answer of -2. And then you go and you look and you say, well, what's the function doing there? It's not even a calculus question. It's kind of like a Math 11 question. Oh, hey, look, the function was actually there. Not that we generally care, but yeah, sure, okay, it's there. And then the last one. Let's look at this situation. So we're going to get near x equals 6. All right. So at the beginning, we're going to be approaching 6, but from the low side, coming in towards the green curtain this way. Looks like we're heading towards 5. And then the next question, 6 plus, let's go in this way on the x's. Following the graph, right? Just following it in. Oh, it looks like we're heading towards a y value of 5. Hey, those both agreed, so we can say the limit is 5. And now, Not even a calculus question, kind of a math 11 question. Oh, what is the function at 6? I don't know. Oh, geez, look, it skips down to a 2. That's fine. I'm not really worried about that in calculus. I want to know where does it look like it was going. All right, next question. Very similar, except we might have to draw the graph first. Okay, and then we can go and answer the questions about the limit. So they're saying, can you please draw this function by piece? All right, so it's just put together in bits and pieces. The first section is built up until 2 and not even quite at 2. So if you imagine kind of a little barrier here, it says, look, don't draw at 2 or beyond. Just draw the graph of y. Okay, again, this f of x, it's the same thing as y. Y is equal to 3 minus x. Well, that's a line that's got a y-intercept of 3 and a slope of -1. And if I need to, I can use my graphing calculator to help me out. But it does kind of look like this. And I draw it up until there, and I'm not allowed to draw it even at 2. That's what this little x minus 2 restriction says. So I might want to say, oh, okay, well, that comes like just up to the moment where that happens. Then the graph says, hey, well, when x is R2, please graph 5. Sure, yeah, if that's what you want. Okay, so at 2, we'll graph 5. Okay, done. And then the last part says, oh, well, after 2, when you're out, past this box, out here, can you just draw the graph of y equals x? It's a straight line through the origin with a slope of 1. So, but only draw it after that box. You're never going to be drawing two functions at the same time vertically. So as I move along here, I'm only vertically drawing this function. I'm going to draw it in green. I am lining my ruler up back at the origin just to kind of figure out where to draw, but I'm not going to draw it back there like that. Okay, that would be wrong. What I want to do is only draw it after this moment where 2 was, so after the 2. So it would look something like that. So if you look, if you kind of move a little bar here along sideways, this is what functions are all about. You're never graphing more than one function at a time. You're either graphing the blue or the orange or the green, right? That's how functions work. Okay, the first question, I can use this as a curtain. First question says, what if you approach 2, but from the high side, right? It's 2 plus. So that's actually along the green path, coming in from the larger than 2x values. And you can say, oh, okay, well, it looks like the limit there, we're heading towards a y value of 2, right? Limits always answer the question, what does it look like the y's are doing? Heading towards 2. B says, why don't you approach that little black curtain but go from the low side? Well, that's following the blue path in, right? The less than 2 part. That looks like we're going to be heading towards a y value of 1. Now the next part says, hey, can you combine those ideas? Could you and just answer the question in general about the limit? We don't want to do this sided things. We don't want to play favorites. Well, they don't agree, so you'd have to say, look, there's just no agreement here. It does not exist. Last one there, part D, says, well, what if you really, really, really wanted to know what the y value was at 2? Not really something that we're worried about with limits, but if you want to look, I guess you pull the curtain away and you go, oh, geez, it's way up there at 5. Has very, very little to do with our work with limits. Okay, so that's the plan for that kind of situation where you have to draw it first. Let's do one more of those over on the next page. So number 14. Got this piecewise defined function. I might use my graphing calculator to help me out. I'm going to draw one picture up until 2 and not even quite at 2. So yeah, before that box, I perhaps use my graphing calculator and say, hey, help me out. And it says, oh, it's a parabola. It's upside down. It's actually got a vertex at 1, 5. And there's a point here. There's almost going to be a point there. And 3, another point there. And so this parabola goes like that. And it stops. And it's not even allowed to graph at 2. This one says, nope, sorry, not at 2. So I might want to go and put a little open circle there. All right. When you're at 2, it says, please graph a y value of 3. Okay, sure. Done. And then after 2, draw the line 6 minus x. It's got a y-intercept of 6 and a slope of -1. So you can line your your ruler up all the way back, but just don't draw all the way back here like that, because you can't be drawing more than one graph at once up and down. So this particular function kind of looks like that. So it actually kind of lines up with where the blue one left off. It would have an open circle kind of as well. But the function doesn't actually follow the rules. It kind of skips down to that y value of 3. Doesn't look like the graphs line up perfectly with their slopes either, something we'll talk about as weeks go by. All right, answering the questions. What if you approach 2 from the high side? Well, that's the green path in, coming in this way. It looks like we're heading towards a y value. Okay, just looking at the y value here on the graph, looks like it's heading towards 4. What if you approach 2 but from the low side? Okay, that's the blue graph, right? That's coming in this way. And it says, what's the y value doing? So again, I'm looking at the y value. Looks also like a 4. And then the next one says, well, could you combine those two ideas? Could you just give us one answer? Sure. It looks like the graph's just plain old heading for 4. And what does the graph do right at the moment when x is 2? That's what part D asks. And the answer is, well, it's not really following the rules. It kind of skips down to a 3. That's totally okay. All right, next limit. I had a little bit of extra space at the bottom of this page, and I needed to throw this one at you at some point. So here it is. This is one that we're simply going to memorize in order to find the answer. I should point out that this memorization deal, this answer, only works if when you play around with your trigonometry, if you're using radians. So I'm going to take my calculator. I'm going to see if I can just do this one numerically. And I'm going to try calculating just what that fraction is for really small x values. But in order to be on the money here, I'm just going to check my calculator. Oh, mine was in degrees. I'm going to switch it over to radians. We do all of our calculus in radians. So I'm going to try taking the sine of, I don't know, some small number, 0.2, and then divide by 0.2. Right? I'm trying to have the x's approach 0. Well, 0.2 is pretty close. Okay, interesting number. But what if I can get closer to 0? So I'm doing this one purely numerically. How about 0.1 divided by 0.1, right? Sine of a number divided by the same number. And it's saying, please use small numbers. Okay, what if we go smaller? What about 0.0007 divided by decimal 0007? See what that does. I think I'm seeing it. I think it's heading towards 1. But wait, we should check numbers on the low side. What about sine of negative decimal 000? I don't know, 4 divided by negative 0.0004. Okay, it's still 1. It looks like it's heading towards 1. And that is the right answer for this. It turns out you can actually evaluate this algebraically if you use that sandwich theorem, the squeeze theorem. But I'm just going to ask you to memorize this one. We won't memorize a lot of stuff for CalCP, but this might be one of them. It will be, when you're at university trying to do this, it will be the sandwich theorem, the squeeze theorem. That's how you actually get there. All right, so that's kind of the theory behind these one-sided limits. Now we're going to see how we can use them just as part of some conversations as we move off to the next couple of pages here, just a little bit more. So you can see from our little note banner on the side here, we're going to talk now about graphs that have vertical asymptotes, like the graph of 1 over x. If you graph 1 over x, it actually looks kind of like this, right? It has a vertical asymptote here, comes down, and then levels off. It's pretty close to that. It has another branch out here. It goes like that. Definitely got some horizontal and vertical asymptotes going on. I want to talk about vertical asymptotes in this page. So yeah, a nice little vertical asymptote here, vertical line at x is equal to 0. And we can actually use left-hand and right-hand limits to just talk with each other about how this graph is behaving at that vertical asymptote. So part A says, well, what do you think the y value is doing, right? So this is the function, right? What's the y value doing when x gets close to 0, but could you approach from the high side? So it's actually saying, could you arrive at x equals 0 this way from big x's, right? Well, bigger than 0 x's. Well, it does not look like it's settling down on one value, right? It looks like it's just exploding. And so you might want to say, well, look, my answer is does not exist. Yeah, that's true. It doesn't. It doesn't have an answer. Or if you want, you can tell people why it doesn't exist. Because it seems to get so big, I can't imagine how big it is. Kind of this notion that we call infinity. So it's heading up to plus infinity, going way up to the top of the sky. The bottom question says, well, what about the limit? What about the y value as you approach 0? But let's go from the underside of 0. So that's coming in with your x's this way, following the graph. You're following this lower branch here, right? Like that. And you're saying, well, what are the y values doing? Well, they're not settling on one answer. So I could say, hey, the answer is does not exist. Or if I wanted to, I can be a little more clear about why I don't think it exists. Because it goes to y values that are so negative, I can't imagine how big they are being negative. And that notion can be written like this. Head down to minus infinity. A negative number so massive, I can't even imagine how big it is. And so this idea of doing these sided limits can help me find and locate these vertical asymptotes. It helps me kind of describe them. So the line, x equals something, I mean, here we had x is equal to 0. Doesn't have to be located there, but this one was. That line is a vertical line, and it's going to be a vertical asymptote. One of those lines the graph gets close to but never touches, of the function if either one of these things is true. If the limit, as you approach a from the low side, gets out of control by either being really big or really small. It could either be plus or minus infinity, up or down, we don't care. Or maybe the graph over on the high side goes totally out of control, either really big or really small. Now it might do both. This graph actually does both. But you might see functions where you only see one branch and you don't actually see the other branch at all. So as long as it's got at least one side of that asymptote where the graph goes up to the sky or just down into the earth, then you can say, that's a vertical asymptote. We can use this to describe it. So let's do that here. Okay, finding some vertical asymptotes for this function. You'll play around with this kind of thing a lot in Math 12. This rational can actually be factored. Factor's pretty nice, x minus 3, x plus 2, and of course that creates some divisions by 0. And divisions by 0 create numbers that are so large we can't even imagine how big they are. And one of them is going to occur when this little binomial down there causes problems at -2, and the other vertical asymptote is going to happen here. And you can just go to your graphing calculator if you want as well. It's totally fine. But we're definitely going to have problems there at -2. We're going to have problems at 3. And this graph, try it on your graphing calculator. Here's what you'll find. When you approach that first red line from the low side as you come in from the left, the graph actually just gets out of control. It just goes whoosh up to the sky. And so you could say, oh, let me tell you about what's happening there. This graph, the limit of it as x approaches -2, but from the low side, the limit of that y value seems to be plus infinity. And then as you check the next section, it actually dives down here like that. So you could say, let me tell you about that. The limit of this graph, the limit of the y values, as x approaches that same -2, but when you come in from the high side, it actually dives down to minus infinity. Okay. Then as I approach that other asymptote, maybe I'll just switch colors here for you. As you approach that other asymptote, it actually dives down here. And you could say, let me tell you about that. The limit of the y values, if you watch the y values, when x approaches 3 but from the low side, that goes down towards the ground to -infinity. And then as you approach 3 but from the high side, you'll see this graph actually goes up like that. So you could say, let me tell you about that. This is what it means to say, describe the behavior, right up in the little example instruction there. That y value seems to go up to the sky. And if any one of those things that happen on any side, you can say, yeah, it's got an asymptote, okay, located at that spot. So that's the deal with vertical asymptotes. You're going to see that as you approach an x value, maybe from one side or the other, the graph goes up to the sky or down into the ground. Now we're going to look at the other possibility. What about horizontal asymptotes? What about when you go off to the side of your page? So we're going to look at limits that happen when x's get really big, right? That's all this is saying, is so big you can't even imagine how big the x's are, to either side of your page. Okay, so if you ever see this, x is going to plus infinity or x is going to minus infinity, this is talking about the extreme, like way out there, the extreme left or right side of your page. So we're talking about, on a piece of graph paper, we're talking about out here, or maybe out here. And if we're talking about x's going to infinity, then we're going to just ignore all this part of the graph in there. Just not really of no consequence to us. We're just looking at the very edges of our graph paper. And you've seen some graphs in grade 11 or math 12 where you've actually got these horizontal asymptotes. So they're flat lines that the graph tends to head towards as you get out to the edge of your page. So I'm going to put in here, okay, my definition, the line y equals b. So this is a horizontal line. Okay, that thing there. Let's try a different color here. Oh, I missed again. One more shot. Got it. Okay, so it's a horizontal line. Y equals a number. That's going to be a horizontal asymptote. If either of these things happen, if the limit of that function as x goes way off to maybe the left side of your graph paper, to negative infinity, that could be some y value that it's heading towards. Or maybe if you go way out here, the limit of the function as x heads towards really big positive numbers, if the y values seem to settle down on one number, you can say, oh, well, that's a horizontal asymptote. This graph here does that. If you actually take a look at it just simply on your graphing calculator, you'll see that it does kind of this shape. It's 0 at the origin, and then it's kind of got an interesting curve to it. It kind of goes like that. And the same thing, it's kind of a reflected even function over on the other side. And so when I go off to the right-hand side of my page or the far left-hand side of my page, way out there, I can see that, yeah, we're approaching, this value of y equals 1. Same thing actually happens out here. And so you could say, oh yeah, there's this horizontal asymptote. Let's call that an HA. At y is equal to 1 over on this side. Actually, same horizontal asymptote over here. Not every function does that, but this one has the same horizontal asymptote on both sides. Just as a caution, you might see some functions in the next little while that will say they have horizontal asymptotes. I'm just going to scribble on this. Maybe I'll go green here. Where they have horizontal asymptotes on one side, and they may cross those horizontal asymptotes in the middle and then have horizontal asymptotes on the other side. Remember, we're ignoring this intersection, and we're saying, well, it should get near that horizontal asymptote at the end. Okay, well, that brings us to this little vocabulary topic here, where we talk about end behavior models. These are just equations that describe what the function's doing near the edge of your graph paper. And let's look at the box, right? It says, okay, the function g is a left end behavior model for f. It's going to describe what happens on the left side. If and only if, definitions always have that little English phrase in there, if and only if. This limit heads towards 1. Now, you might look at this. This is perfectly fair to look at this and say, geez, why did the math people write it like that? Why didn't they just say this? Why didn't they say, oh, well, if your graph, your actual graph, f of x, seems to be agreeing with this graph, g of x, when x heads towards negative infinity, when you go way off to the left side of your graph paper. You just multiply, top and bottom by g, right? Well, it turns out that, maybe the function g doesn't exist, and maybe f doesn't quite exist, but if you divide, then it does. Math people are very picky about making sure they've got something that will be bulletproof. It'll work every time. But even though they're not saying this, this is kind of the idea. Okay, so it's not exactly that. Math people would say, don't write it that way. But this is the notion that the two things should be heading towards the same value. That way, if you divide one by the other, you get to 1. And then the same thing with this right-hand behavior when you go out to the right side of your page, right? This negative says we're going left, and a positive there says we're going to the right. It's kind of, you look at that and you're like, what is that talking about? Well, let's just go and draw kind of a weird graph of f of x. Like maybe start down here, then throw some wiggles in it, and then settle down on something like that. This might be my graph of f of x. That might be my actual function. And it might be really complicated on the inside. But maybe there's some function, what are they calling it, h for the right-hand side? Maybe there's some function h of x where it doesn't work well in the middle of your graph, but maybe near the end of your graph paper, maybe these two functions are kind of getting right near each other. They're kind of sharing the same y value. And you could say, well, I know h of x doesn't look like it matched up f of x, over here, but as you get near the far edge, as you go way out to x being super big, it seems to match it up really nicely. And you could do the same thing over on the left. You could say, well, geez, that blue graph, the actual graph f of x is very complicated, but it seems like when I get near this side of my graph paper, it's doing a pretty good job of just matching up this nicer graph, this simpler graph that I've got called g of x. And it might be nowhere near g of x in the middle of your graph paper, but as you head way off to this side, when x's go way out to negative infinity, maybe the two graphs, the green and the blue, start to kind of lie on top of each other. And you can go, hey, look, that green one does a nice little description of what the blue one's trying to do. That's what we mean by end behavior. We're saying, oh, the blue one behaves like the green one, or the blue one behaves like the orange one when you go off to the right. Why would you want to do this? Well, sometimes those blue or orange functions might be much simpler to work with than the complicated blue one. So that can be a powerful thing to have some simpler description, even if it only works off of the edge of your page. Okay, one last page. Let's continue on talking about this limit deal when x's get really big. And we're going to look at some end behaviors for these fractions here to see what they do. For example, 3, at least for a, b, and c, we've got some fractions. And I'm just going to put a little note in here about what you can do to try to find end behaviors for fractions. So I'm just going to say in here, for fractions, rational expressions, people would say, you can try watching the dominant terms. This works fairly well. So for example A, I've got this fraction, and in the middle of my graph paper, I have no idea what this thing's going to look like. I really don't. But when I get near x being, this is the whole plan, right? Is to say, hey, well, what happens when the x gets really big? When you have x's that are, 1,000 or bigger, then 1,000 squared is way stronger than just the 1,000 that's here, or stronger than 5. So when you get near the edge of your graph paper, this term in the top dominates the other terms in that numerator. It does not dominate them near x equals 0. In fact, the 5 is the biggest thing. But once you get past, like about 100, you might as well only be looking at the 4x squared. And the same thing down in the bottom. You can look and say, hey, what's the strongest term when the x's are big? X cubed is way stronger than x when the x's are big. And you can say, this function f of x, it's probably going to be feeling kind of like a 4x squared sitting on top of a 2x cubed. It's not that, but it's going to be awfully close to it. Those will be the most important terms. And if I look at this, we've actually got a degree in the bottom that's bigger than the top. So I'm just going to leave a little note here that the bottom degree is actually bigger. Okay, bigger than the numerator. We're going to see that that causes this to happen. My end behavior, pick a color here, maybe orange, new function, it's not f of x. These graphs will not always lie on top of each other, but near the edge of your graph paper, hey, let's tidy this up. We can reduce it. We could just call that 2 on top of x. near the edge of your graph paper, you might as well just be graphing 2 over x. It's going to look just like that. And 2 over x has a nice little horizontal asymptote. It's actually got a horizontal asymptote of y is equal to 0. So near the edge of your graph paper, expect this graph to head down towards y equals 0. It's going to beautifully follow this function here near the edge of your graph paper. Okay, trying the next one out. Dominant term here would be 10x cubed. Dominant term here would be the 5x cubed. And so we've actually got, for big x values, really only a need to look here. 10x cubed on top of 5x cubed. So for big x values, you might as well just say, hey, this thing's going to have an end behavior that, so let's reduce. Well, it's just 2. Just plain old 2. Okay, so here the bottom degree is equal to the top degree. This graph will head towards just graphing 2. And it's going to have a horizontal asymptote, of course, at y equals 2. It'll do that near the edge, the left and the right-hand side of your graph paper. What if the top degree is bigger than the bottom here? 6x to the 5th on top of a 2x cubed. When you get near the edge of your graph paper, okay, only near the edge, for really big x values, you might as well only be graphing 6x to the 5th on top of 2x cubed. Those will be the important terms. And you could say, hey, you know what? The end behavior for this thing, if I wanted an end behavior graph that's a little simpler than that messy fraction of algebra called f of x, I can reduce even, and I could say, why don't you just graph 3x squared? And you'll find that the graph really nicely follows 3x squared near its edge. That's its end behavior. It's just going to look exactly like a parabola near the edge of the graph paper. Near the middle of the graph paper, all bets are off. But near the edge of your graph paper, it just looks like a nice little parabola. Yeah, let's just try that one out. I don't know if this will work very well, but I'm going to give it a shot. I'm going to try graphing that original function, that messed up one there. Use some brackets here, 6x to the 5th minus an x plus a 1, that's my numerator, and then in the bottom 2x to the 3. Okay, and I can try graphing various zooms here. I'll start off near the center of my graph paper. How about zoom 4? Okay. Yeah, okay. Weird. Very complicated looking function, right? That does not look like a parabola. Not at all. Now let's try zooming out a little bit. Okay, still kind of complicated. I'm going to try zooming out a little bit more. So I'm going to make my window go from maybe minus 40 to 40, maybe tick marks every 10. I'm going to expand my y's a little bit because it was getting hard to see. So I might go minus, I don't know, 1,000 and 1,000. Tick marks perhaps every 100. I just want to show you what happens when we look way near the edge of your graph paper. So we're way out here now at 40 and minus 40. That is the same function. If you zoomed in, it's all squiggly and crazy near the center. Now, here's the end behavior. I'm going to graph this g of x. How about I graph 3x squared? Maybe I'll graph it thick so you can see it a little bit larger. Yeah, near the edge of my graph paper, it looks exactly the same. In here, no way, right? Zoom 4. Here's the actual function. Weird. And here comes the parabola. It does not look like the parabola in the center, but on the ends it does. That's all we mean by end behavior. All right, last one. Let's just talk about exponentials here real quick. Got this function, x plus e to the x. We'll graph that one correctly using some end behaviors down here. We'll figure out what they might be. But let's first just look at e to the x. So e is a number of more than 2 and less than 3. And if you graph e to the x, it looks like this. It's very small here, and then it just explodes. So some people say it kind of looks like a hockey stick, right? It has a weak side when you have negative values going in for that exponent, and then it has a very strong side. So it's important to know that when you start thinking about end behaviors. If you're trying to graph this, f of x is equal to x plus e to the negative x. Okay, so that means that this part here is actually going to be this graph but flipped, right? It's kind of a math 12 thing. So we're going to flip, left to right. That's what e to the negative x would look like here. Help you out here real quick. Clear those off. We'll just do a quick little graph of e to the x. Zoom 4. Here's e to the x. Looks like a hockey stick. And if you were to graph, instead of that, this e to the minus x, that's going to flip that around. It flips the strong and the weak sides. So there's the graph of e to the negative x. It's very aggressive out here. Very aggressive. Stronger than any power. And it's super weak in here. And so if somebody said, hey, well, what do you think the graph of this thing might look like? Well, I might do some end behaviors. I might say that, you know what? Over here, my end behavior might be y is equal to e to the negative x. That's the strong one. And if you graph e to the negative x, okay, it looks like that. So out here, this graph is probably going to look kind of like this. But over on the other side of the page, my end behavior here, well, who's strong out here when the x's are big and positive? Not that one, right? That e to the negative x is so weak out there. But x will actually be stronger than the exponential out there. So if I graph y equals x, that kind of looks like this. Well, maybe not curved. Try that again. Like that. So if people said, well, what's your best guess on what this graph's going to look like? I don't know. But on the edges, it's going to kind of follow those. And, you know, you actually do the graph of this, and you'll see that, yeah, it really follows that one out here, and then follows this one here. That's all end behavior is talking about. And we can use these sided limits if we want, right? We can say, oh, x is going towards plus infinity when I want to talk about this side, or x is going towards negative infinity if we want to talk about that side. And that finishes up our lesson for today.